Oh, so hello everyone. I'm Himanshu Vasnani from Department of Mechanical Engineering. I'm here to present a lecture on the subject material science. The code is ME207, unit number 2, lecture number 10 in the series. Today's topic are creep stages and phase diagram terminology. So here we are going to study about creep behavior, different stages of creep diagram. Then study about various terms that are used in phase diagram like solvent, solution, etc. So today's objective is to provide students the basic understanding of creep stages, phase diagram terminology, and the outcome will be students have learned the basics of creep stages. Students have understood various phase diagram terminology. So these are the topics that we need to discuss today, and these topics are important from understanding point of view. So especially the student understood various phase diagram terminology. So these terminologies are important. So let us start with today's diagram. Sorry, today's lecture. So creep. Materials are often placed in service at elevated temperatures and exposed to static mechanical stresses. Example, these turbine rotors in jet engines and steam generators that experience centrifugal stresses and high pressure steam lines. Sorry. So you know that there are materials, there are some applications in which the materials they are uh, placed at such a position while servicing that they are exposed to mechanical stresses, that is, they have a static mechanical stress applicable on them and at particular temperatures. So these kind of materials they are prone to a defect called as creep. Now deformation such as under such circumstances is termed as creep, uh, which can be defined as time dependent and permanent deformation of materials. Okay, so we have to understand that uh, if any application like turbine rotors in jet engines, okay, like these are you can say prone to such kind of deformations like creep. Okay, so defined as the term dependent and when subjected to a constant load or stress. Creep is normally an unfavorable, undesirable phenomenon and is often the limiting factor in the lifetime of a part. Obviously, if it will lead to permanent deformation, that it means that it is an undesirable phenomenon. Okay, and will obviously lead to you can say is a limiting factor in the lifetime of a part or a machinery, whatever. It is observed that in all materials types, like for metals, it becomes important only for temperature greater than about zero point 0.4, that Tm. And Tm is absolute melting temperature. So this is a general introduction of creep. As well as creep behavior. A typical creep test consists of subjecting a specimen to a constant load or stress while maintaining the temperature constant. Deformation or strain is measured and plotted as a function of elapsed time. What happens in this that in a creep, okay, in this what happens the workpiece or the specimen, it is subjected to a constant load, okay, or stress while maintaining the temperature constant. At that time, some deformation takes place with time. Okay. Now in the coming diagram, which shows representation of a typical constant load behavior of metals. So you can see in the coming diagram, you will see that upon application of load, there is an instantaneous deformation. Okay, which is mostly you can say somehow elastic and then permanent. So here in this diagram, you can easily understand and see that the whole you can say creep process. is divided into three stages, like one is primary, then secondary, and tertiary. This diagram is normally called as creep curve. Okay, in this, what happens? There is a creep strain versus time at constant stress and constant elevated temperature. You can see on the x-axis you have the parameter of time, and there is TR, rupture time, and on the y-axis you have creep strain. So there is this is called a creep curve of strain versus time at constant stress and constant elevated temperature. The minimum creep rate, that is delta E upon delta T, is the slope of the linear segment in the secondary region. Rupture lifetime, that is TR, is the total time to rupture. Okay, so you can see that there are three stages in which the whole process from starting to ending where the rupture happens is divided. So this is called as a creep curve. We're talking about this creep curve only in this figure. So you can see that upon application of load there is an instantaneous deformation. So let's go further. Then the resulting creep curve, it consists of three regions, each of which has its own distinctive strain time feature. The first one is the primary or the transient creep. Okay, the first phase. This occurs first, okay, amplified by a constant continuously decreasing creep rate. That is, the slope of the curve diminishes with time. Okay, the slope of the curve diminishes with time. This suggests that the material is experiencing an increase in creep resistance or strain hardening. So deformation becomes more difficult as the material is strained. In the primary curve creep, what happens? The slope of the curve, it diminishes with time. Okay, in this what happens? The deformation becomes more difficult as the material is strained. This is the first, you can say, uh, process, like in the creep curve, called as primary or transient creep. Now the second and the important, that is secondary creep. It is sometimes termed as steady state creep. There is another name for this called as steady state creep. In this the rate is constant. Okay, the rate is constant. That is, the plot becomes linear. This is often the stage of creep that is of longest duration. I show you the diagram. You can see in the diagram the whole creep curve divided into three different stages: primary, secondary, and tertiary. The secondary stage is the longest, okay, stage in out of these three stages of the creep curve. Okay, so it is saying the same, that this curve has the longest duration. See, here it is having the longest duration in the middle. The constancy of creep curve is explained on the basis of a balance between competing processes of strain hardening and recovery. I repeat, the constancy of creep rate is explained on the basis of a balance between the competing processes of strain hardening and recovery, in which recovery being the process whereby a material becomes softer and retain its ability to experience deformation. Okay. Now, after the secondary creep, there is a there is the third stage calling tertiary creep. Okay, in this tertiary creep, it is, you can say, the third stage and the final stage at which after which the rupture happens. Okay, in this what happens? There is an acceleration of the rate and ultimate failure. This failure is frequently termed as rupture. So here, due to the application of constant stress and constant elevated temperature during the service time or working time, what happens? The workpiece experienced creep, and this is divided into three stages as shown in the creep curve of strain versus time diagram. Okay, so you can easily now get up that in out of the these three stages, the secondary stage is the longest one, and the last stage, that is the tertiary stage, is the final stage in which the rupture obviously takes place. Here in this, the rupture lifetime TR is the total time to rupture, which is very important. It may be in, you can say, minutes, or it may be in days, or it may be in years. It depends upon. So, uniaxial compression tests are more appropriate for brittle materials. These provide a better measure of the intrinsic creep properties in as much as there is no stress amplification and crack propagation, as with tensile loads. Okay, so this is the, you can say, understanding that for compressive materials, you can, sorry, for brittle materials, compressive tests are more effective. Uniaxial compressive tests are more effective. Okay. Now compressor test specimens are usually right cylinders or parallel pipe having length to diameter ratio ranging from about 2 to 4. For most materials, key properties are virtually independent of loading conditions. So here we understand that or what importance the sleep has. So possibly the most important parameter from a creep test, one of the most important parameters on the creep test is the slope of the secondary portion of the creep curve. Okay, the secondary stage. Okay, it is also called as the minimum or steady state creep rate. Okay, now it is the engineering design parameter. Let me show you this again. The second phase, you can see in this diagram also the secondary stage. It is called a steady state creep. Okay, steady state creep. You can understand, and it may be useful to you. And it is the engineering design parameter that is considered for long life application, such as the nuclear power plant component that is scheduled to operate for several decades, and failure or too much strain are not options. Understood. So it is, you can say, an important engineering design parameter. Okay, because this is considered for applications that require long life. They have given an example that for a nuclear power plant component, it is uh, it is pre-planned, or it is scheduled that it will, the component that we are designing for nuclear power plant or for a particular application, it should operate for several decades. Okay, so and failure or too much strain are not options in this case. On the other hand, for many relatively short life free situations like turbine blades in military aircraft or rocket motor nozzles, time to rupture or rupture lifetime is a dominant design consideration, which is also indicated in the. Okay, so there is long life required also, and there is somehow that also. Of course, the what is determination. Okay, of course, for determination, creep test must be conducted to the point of failure. The creep tests that are there must be conducted to the point of failure. They are termed creep rupture test. Because what happens that whatever we are doing, we are going for to produce a part for application. And for proper experimentation, we should know that if you are conducting creep test, then it should be conducted you don't have you can say, and these we can say tests are termed as creep rupture tests. Just a knowledge of these key characteristics of a material, okay, this all these features that we have discussed allows the design engineer to ascertain its suitability for a particular application. Obviously, the design engineer who is designing all such arrangements is who is designing all such setup, all such arrangements, is bound to know these all such suitable conditions for a specific application. Now, stress and temperature effects. See, this is also an important, you can say, factor. characteristics you can say. Okay, so both temperature and the level of the applied stress influence the key characteristics. Okay, can I show you the diagram 29? This is diagram that is influence of stress and temperature on creep behavior. So in the C, you can see on the axis you have time, and in the y-axis you have creep string. And there are four different colors showing yellow, green, blue, red, and in which you can see there how the stress, which is stress is greater, which is lesser, and then which is the least. And according to that, you can see the temperature, which temperature is better or higher, either T3 or T2 or T1. Okay, so this curve shows the influence of stress and the temperature T on creep behavior. So in that at a temperature substantially below than zero point 0.4 of T, and after initial deformation, the strain is virtually independent of time. So with either increasing stress or temperature, the following will be noted. The first one is the instantaneous strain at the time of stress application increases. The instantaneous strain at the time of stress application it increases. The steady state creep is increased and the rupture lifetime is diminished. Okay, this is somewhat different thing. So you should understand with increasing stress or temperature, the following points will happen like inserting the strain at the time of stress application will increase automatically in the steady state creep. Okay, then the steady state creep is increased and the rupture lifetime is diminished. So in the diagram also you can see how the temperature and the stress are described. So alloys for high temperature use. So there are several factors that affect the key characteristics of metals. These include melting temperature, elastic modulus, and grain size. Okay, the factors which affect the key characteristics of a materials include like melting temperature, elastic modulus, and grain size. In general, the higher the melting temperature, the greater the elastic modulus. You can see the relationship. The greater the elastic modulus, and larger the grain size, the better is the material's resistance to heat. Larger grain size, the better is the material resistance to creep. You can understand the role of melting temperature, elastic modulus, and grain size for creep. Grain size is larger, it will material will provide resistance to creep. Okay. For if you have the high melting temperature, automatically the elastic modulus will be high. So in this way, you can understand what is the role of these three terms when you go for creep characteristics. So relatively low grain size, smaller grains permit grain boundary sliding, which results in higher heat. This effect may be contrasted to the influence of grain size on the mechanical behavior at low temperature. Okay, influence of grain size to the mechanical behavior at low temperature. That is increased both in both strength and toughness. So here you can understand that what is you can say the factors or the characteristics we then should take care. Okay, then stainless steel or refractory material and super alloys are especially resilient to creep and are commonly employed in high temperature service conditions. Okay, you can understand that various industries like these are resilient to creep. Okay, and are commonly employed in high temperature service condition. The key resistance of the cobalt and nickel super alloys is enhanced by the solid solution alloy. Okay, the of cobalt, key resistance of cobalt and nickel superalloys is enhanced by solid solution alloy and also by the addition of a dispersed phase that is virtually insoluble in the matrix and also by addition of a dispersed phase that is virtually insoluble in the matrix. Okay. And in addition, advanced processing techniques have been utilized. One such technique is directional solidification, which produces either high elongated grains or single crystal components. And another is the controlled unidirectional solidification of alloy. I repeat, controlled unidirectional solidification of alloys having designed compositions wherein two-phase composite results. I repeat it once again. Another is the controlled unidirectional solidification of metals having specially designed compositions wherein two-phase compositions wherein. Okay, so here you can understand that uh, what the key resistance is giving, how it is, you can say. So we have a question for you, some simple two questions. The one is what happens when we attach a heavy weight to a wire at relatively low temperature? So the answer will be the wire snaps right down right away. So another question is the what happens when we hang a lighter weight from a wire at a higher temperature? It says at first seems nothing, the weight is just hanging there. Under some circumstances we may after seeing several years or for several days, several weeks, whatever they say, several work for hours later, and find that the weight has gradually stretched the wire after calculating the initial and the final, you can say, wire length. This deformation at elevated temperature, this deformation in which we find that the wire is stretched, this deformation at elevated temperature under constant load, the load is constant, is called as creep. Now it depends upon the wire material and temperature of the load. Okay, so here you see that how the wire material and temperature are responsible for. Okay. Then creep strength and alloys. The creep strength is commonly used together with rupture strength, which is the stress at which rupture is produced under certain environmental conditions and for a specific period of time. Like being essentially a measure of the material resistance to creep deformation. Creep strength is reduced from the material's ability to resist microstructural dislocation movement. Okay, I repeat once again, then you understand the words. See, being essentially a measure of the material resistance to creep deformation. To deformation to happen, you need to measure the material's resistance. Okay. So here what is then being essentially a measure of the material's resistance to creep deformation. Creep strength is reduced from material's ability to resist microstructural dislocation moment. That's why it is also referred to as creep resistance or creep limit. In steels, for example, creep strength becomes significant only at high temperature. In steels, creep strength becomes significant only at high temperature. Alloys, particularly aluminum alloys, are prone to creep fatigue and fracture due to their low melting point. However, there are other factors that affect the creep strength of alloys. Okay, that I will show you other factors also that affect the creep strength of alloys. So I'll show you that. The first is substructure composition. Okay, these are like a stable substructure that has uniform dislocations, provide resistance to creep fatigue. However, a substance that worsens under strain will result in reduced creep strength. Okay, then nickel-based alloys are a good example of this. A fine grain size in the structure can also increase creep strength, and vice versa, as smaller grain size are coupled with stronger material properties. Okay, so we have to understand this also that substructure composition is also okay. Then heat treatment. See, us in this we know that in a stable structure that has uniform dislocations provide resistance to creep factor. Okay, that is it. Now heat treatment tends to creation of austenites. Some of these, such as bainite, help to increase the creep strength. Okay. In the heat treatment, what happens that it will lead to creation of austenites, and some of these, such as bainite, helps to increase the creep. Now, soil solution strengthening it lessens movement and deformation through the lattice structure. That is, molybdenum increases creep strength significantly. Okay, molybdenum increases creep strength significantly. Now, hard precipitate quantity and dispersion like carbide. You can go with that. The carbides and intermetallics such as vanadium carbide, when dispersed finely and evenly in an alloy, reduce movement and creep. Therefore, the creep strength inherent in an alloy differs considerably depending on the chemical composition, the spacing of particles in the materials, and the treatment or strengthening of the matter. Okay, so you can understand that the creep strength, okay, it also you can say differs depending upon the chemical composition and the spacing of particles in the material and how the treatment or strengthening of material is done. Okay, then you can see the list, a list of different you can say materials, okay, with their corresponding creep strengths, and there you have given a relative temperature and various applications. Okay, like for example, if you go with material that had dispersed hardened platinum 10% root is the technical name of the material. So here you can see the creep strength is 5.6 and temperature is 1200 degrees centigrade, and applications are equipments for glass and ceramic industry. Now in second material is like Inconel 690, you can call as VDM at the rate alloy 690. Okay, so this element has creep strength of 56, temperature of 700 degrees centigrade, and applications like a treatment of radioactive waste boilers from steam generators are pressurized water reactors. So this is also an important, you can say, table showing different materials and their heat strength and their temperature and their application. You can see the difference in the applications. So much, you can say, industrial. Then again, for usually for the another material like alloy 286, it has a heat strength of 385 and temperature of 650 degrees centigrade. So it can be used in bolts, in fasteners, in turbines, in castings. And another material that is called as Inconel 625. Okay, like medium at rate alloy 625. The technical name is Inconel 625. It is having heat strength of 440 and temperature of 600 degrees centigrade. It has applications for production of super phosphoric acid offshore industry. Okay, now the next material that is seen, that is Virium as an alloy 716 or Inconel 718 or Inconel 718. So it has a huge strength of 810 and temperature of 550 degrees centigrade. This is like the static and rotating parts, rotating components in aircraft turbines and stationary terrestrial spacecraft. Okay, spacecraft. So then the comes the measurement of heat strength. So till now we studied about creep, different stages of creep, and other sorts of things related to creep. Okay. Then there is you can say measurement also. If you want to measure, you can measure the creep strength. Okay. Now creep strength is generally is measured Using the creep testing machine, a device that measures the distortion of a metal at various stress levels. Okay, it can be used to plot how much stress and strain a material can take, with temperature or loading as variables. Okay, so you can see the resulting graph will show three stages of creep, namely primary, secondary, and creep, primary creep, steady state creep, and tertiary creep. Okay, the graph can be assessed to pinpoint the temperature and time interval for the various stages of creep. The creep strength or creep limit can thus be ascertained from the tertiary creep stage of the graph. Okay, the creep strength or creep limit can be thus be ascertained from a tertiary creep stage of the graph. Now it is crucial to control the temperature of the chamber within which the creep test is performed. Okay, in order to keep the effects of thermal expansion minimal. Now, how to minimize or avoid creep deformation? It is clear that the generally an undesired phenomenon that we studied in the first slide only. And in order to reduce its effect on or prevent it from certain design consideration can be taken into consideration. Some of which are minimize grain boundary sliding by using single crystal materials with large grains and remove microstructural vacancies via adding solid solutions. Use materials with high melting points. Then minimize diffusivity by using face-centered cubic FCC metals rather than BCC metals, the body-centered cubic metal, due to their lower diffusion coefficient. Okay. Use material with high shear modulus or make use of convenient alloying to reduce the working temperature at which the material is utilized, like application specific. So this through these things you can minimize or try to avoid creep because this deformation is time dependent and it occurs maybe in a very long time. So you can understand that the how what the working temperature is important. Okay, and obviously in the industry everything has a cost. If anything deforms, then it need to be replaced, which leads to some spending of you can say uh, funds. Okay, so we need to economize our funds by taking care of you can say part or machinery. So next, now we are going to start with the phase diagrams. And today we'll go with the terminology part. Okay, the terminology part is important because uh, before studying all the kinds of phase diagrams, we should know some terms which will be useful to you in the coming lectures. Okay, the understanding of phase diagram for alloy system is extremely important because there is a strong correlation between the microstructure and mechanical properties. And the development of microstructure of an alloy is related to the characteristics of its phase diagram. In addition, phase diagrams provide valuable information about melting, casting, crystallization, and other phenomena. Okay, what happens that if you want to understand the phase diagram, okay, you see that there is a strong correlation between microstructure and mechanical properties. Okay, so you can understand the development of microstructure of an alloy is related to the characteristics of its phase diagram. Okay, because what happens is that when we go for phase diagrams, it will give you information like for melting, what temperature is required, you can say for casting, for crystallization, other phenomena also. So phase diagram is that much important. So starting from the thing, the various definitions or terms are like component. The term component is frequently referred to pure metals and are compounds of which an alloy is composed of, which is the alloy is made up of all the metals or compounds, which is you can say referring to that only. For example, in brass, the components are copper and zinc. So you should understand what do you mean by a component when it comes in terms of phase diagram. That it is, you can say, composition of a particular alloy. Okay. Then solute and solvent. The solute and solvent are terms that are commonly employed. Like solvent represent elements or compound that is present in the greatest amount. Okay, so these solvent atoms are called as host atoms because they are present in great amount. Solute, on the other hand, is denote an element or compound present in minor concentration. So it is called as solute. For instance, solvent has its own importance and solute has its own importance. Then system. The term system has two meanings. First, system may refer to a specific body of material under consideration. Example, a ladle of molten steel. Or it may relate to the series of possible alloys consisting of same components but without regard to alloy composition. Example, the iron carbon system. Okay, the term system has two meanings. One is system may refer to a specific body of material under consideration, that is the system, a ladder of a model. Another in or it may relate to the series of possible alloys consisting of the same components. Series of possible alloys consisting of same component but without regard to alloy composition, like iron carbon system. Okay, which is called as a system. Now solid solution. See, in this case, what happens that in this case, two metals are completely soluble in solid as well as in liquid state. We have same type of lattice and critical atomic size. Copper and nickel form an isomorphous system. Okay, copper and nickel forms an isomorphous system. The concept of solid solution. Okay, you can see the third point. The concept of a solid solution consists of atoms of at least two different types. Solvent atoms become or we can occupy either substitutional or just interstitial positions in the solvent lattice, and the crystal structure of the solvent is maintained. Okay. And the third is in addition of impurity atoms to a metal will result in the formation of a solid solution or a new second phase depending on all kinds of impurity, their concentrations and the temperature of the alloy. Okay, this is how solid solution is formed. A solid solution forms when as the solute atoms are added to the host material, the crystal structure is maintained and no new structures are formed. Perhaps it is useful to draw an analogy with a liquid solution. If two liquids may be soluble in each other, such as water and alcohol, are combined, a liquid solution is produced as the molecules intermix and its composition is homogeneous. We are using alcohol and water. Alcohol is another color, water is another color, but when you mix them, they go under molecule intermix and the composition is also, you can say, throughout homogeneous. Okay. Then a solid solution is also compositionally homogeneous. The impurity atoms are randomly and uniformly disposed within the solid. So these are the some properties of solid system. Okay, solid solutions. Okay, we have studied about component. We studied about uh, solute and solvent, we studied about system, we studied about solid solution. Then next we go for eutectic type. When two metals are completely soluble in the liquid state but partly or completely insoluble in the solid state is termed as eutectic type. Like aluminium carbon, aluminium iron carbon, aluminium manganese. So they form a eutectic system. Okay. Then peritectic type. Now in this case, what happens is the case liquid and solid. In this case, liquid and solid combine to form a new solid. The melting point of two metals differ considerably. You can, for example, Ag and Bt form such type of such a system. In the eutectic system, the crystals of beta solids solution precipitated at the beginning of solidification react with the liquid alloy having definite composition to form new crystals of alpha solid solution. Okay, now in the peritectic type that we are studying, what happens in type? The solid and liquid combine to form a new solid. Now two phases that are used to produce one different phase with reaction just the opposite of eutectic reaction. Now the peritectic reaction similar to other systems of solidification of different matter but is comparatively less common. Okay, this reaction also occurs at constant temperature. So we can say that liquid plus solid. Okay, solid one, like on heating and cooling, you will get a new solid and solid two. Okay, yeah, liquid plus beta, and upon hot cooling and heating, you get an alpha. So the temperature at which the peritectic reaction occurs is noted by TD. Okay, the TD phase disappears upon completion of, you can say, transformation, obviously. And they are given an example of ETAG, example of peritectic reaction. There is also peritoctoid reaction. In this, what happens? In the reaction of two solids turn into a third solid. So you can say that alpha is beta equals to on cooling, on heating and cooling, you get uh, okay. On reaction of two solids, you get a third solid. Monotactic type. So in this case, two liquid solutions are not soluble in each other, and over a certain composition range, there is a miscibility gap in liquid state between the two metals. So in this type, one liquid decomposes into another liquid solid. Okay, then like copper and lead are forms monotactic system. Okay, one liquid decomposes into another liquid solid. So you will get an input. Ah, then you can take eutectoid type. And in this, what happens that one solid decomposes into two different solids. Obviously, solid to solid deformation takes place, like iron, carbon, copper, zinc. Yes, we etc. They form eutectoid system. Eutectoid transformation takes place at constant temperature, and products of transformations are present as intimate mixture having appearance in the microscope. I repeat, electrode transformation takes place at constant temperature and the products of transformation are present as intimate mixture having appearance under the microscope. Electrode reactions is of the form like gamma is equals to 1 heating and cooling we get alpha plus. So the electrode structure frequently lamellar sorry, is produced by the precipitation from the solid solution. The crystal structure of new phase is known as Weidman-Stern structure. Okay, the Jeter reaction is an iron carbon diagram in which austenite, a solid solution, is decomposed into pearlite. Okay, it decomposes into pearlite. The most important example of decomposition is heat treatment of steel. Okay, so here you can understand how things work. Now solubility limit. This is also an important term, so we need to discuss using it. So for many alloy systems and at some specific temperature there is a maximum concentration of solute atoms that may dissolve in the solute to form a solid solution. This is called as solubility limit. I repeat once again, for many alloy systems and at some specific temperature there is a maximum concentration of solute atoms that may dissolve in the solvent to form a solid solution. This is called as solubility limit. Now, in addition to solute in excess of its solubility limit, results in formation of another child solution, another solid solution or compound that has a distinctively different composition. So, for illustrating this concept, consider a water sugar system. Okay, you know that sugar is added to a water, then a water system, or you can say a syrup forms. So as more sugar is produced, the solution becomes concentrated under the solubility limit is reached, and the solution becomes saturated with sugar. This is the kind of a solubility limit. At this time, the solution is not capable of dissolving any more sugar, and other additions simply settle to the bottom of the container. So the system now consists of two separate substances, a sugar water syrup liquid solution and a solid crystal of undissolved sugar. So the solubility limit of sugar is developed before in water depends on the temperature of the water and may be represented in graphical form on a plot of temperature along the coordinate and composition. Okay, like along the abscissa. Now the along the composition axis, increasing sugar concentration is from left to right and percentage of water is from right to left. Since only two components are involved, sugar and water, the sum of the concentration at any composition will be equal to 100%. Okay, like you can see the diagram. Yeah, this is the diagram showing the solubility of sugar in a sugar water syrup. You understand on the axis you have weight, percentage of composition in that, how water is added and then how sugar is used. But after a particular temperature, you can understand there is solution, the solubility limit. Okay, so let me explain this. The solubility limit is represented by nearly vertical lines in the figure, like for composition and temperatures, as to the left of the solubility line, only the syrup liquid solution exists, and to the right of the line, the syrup and solid sugar coexist. The solubility limit of some at some temperature is the composition that corresponds to the interaction of the given temperature coordinate and the solubility limit line. For example, at 20 degrees centigrade, the maximum solubility of sugar in water is 65%, 65.8%. So as the you can say the figure solubility limit increases slightly with rising temperature. You can see here also. The on the right hand side there is temperature given. You can see as temperature is increasing, the solubility limit is also increasing. Okay, so you can understand that how temperature is with the composition here in this by just looking at this diagram only. Okay, now phases. So a phase may be defined as the homogeneous portion of a system that has uniform and chemical properties. Every pure material is considered to be a phase. For example, the water sugar syrup solution discussed above is one phase and the solid sugar is another. Each has different physical properties. One is a liquid, other is a solid. So each is different chemically. That is, it has a different chemical composition. Like one is virtually pure sugar, and another is a solution of water and sugar. So we need to understand the phase. Okay, we need to understand the phase. Now, if more than one phase is present in a given phase system, each will have its own distinct properties and a boundary separating the phases will exist. Okay, across which there will be a discontinuous and abrupt change in the physical or chemical characteristics. When two phases are present in a system, it is not necessary that there will be a difference in both physical and chemical properties. A disparity in one or the other set of properties is sufficient. So now let's start with the quiz phase that we are about to discuss. Now the first question is that following is wrong about the phase diagram. Although this code is something wrong, that it gives information on transformation rates or written amount of different phases can be found in the given equilibrium conditions, or it indicates the temperature at which different phases start to melt, or solid solubility limits are depicted by it. So the answer is A. Yes, it gives information on transformation rate. Now second MCQ, in creep curve, which are the following stages known as the unstable stage. So at this stage the transient creep stage is the unstable stage. Sorry. In creep curve, in which of the stages do we observe a constant deformation rate? So it is called as the steady stage creep stage. Okay. In this you can see that we observe a constant deformation rate, the steady state creep stage. In creep curve, in which of the following stages do the deformation rate increase more? You can understand the fracture stage. The last stage in which the fracture happens is called the fracture stage. The specific body of materials. You can understand there are in the creep curve there are three stages, no? Primary, secondary, and tertiary. The third stage, which is called the fracture stage. So specific body of materials or a series of alloys with the same composition is known as you can call it system. Okay. Then time dependent yield is known as creep. Then the maximum concentration of solute that can be added is defined as solubility limit. Okay, we discussed this about this. Now it is used to denote an element of a compound present in a minor concentration in a solution solute. Okay, minor concentration solute. And when two metals are completely soluble in the liquid state, but partly or completely insoluble in the solid state, this whole system is termed as reactive type. Now, which are the following? You understand this? Okay. Which of the following is a slow rise of plastic deformation under action of stresses? Which of the following is a slow rise of plastic deformation under action of stresses? Pretty easy. Okay. So I think you might have understood this all MCQs, and you can refer these books if you want to. You can say uh, go and extend your knowledge beyond the PPTs and refer this. So for now, thank you all.